Hello, this is Ra Khalid from the University of Girona, and I'm glad to have this opportunity to present our work on the deep learning-based segmentation of breast lesions in DCE-MRI. Now, dynamic contrast enhanced MRI is an effective tool to diagnose breast cancer since it allows to differentiate cancer tissues. For example, as we can see here, cancer tissues appear differently than normal tissues in the post-contrast scans. And also the TIC, the time intensity curve of cancer tissue, is distinctive, as shown here in red, from the ones of normal tissues, shown here in green. So usually the curve of cancer tissues is characterized with this rapid increase in intensity, reaching a maxima, then followed with this rapid washout. The main goal of our work was to segment breast lesions in 3D DCE-MR images since it's an important preliminary step for breast cancer CAD systems. And automizing this task helps to avoid all the disadvantages of the manual segmentation. Moreover, the motive behind using deep learning was the fact that there's only a few works on this task using deep learning. Most of the existing works were using other methods like traditional machine learning methods. We used 46 cases from a public dataset. For each case, there was one pre-contrast and 4 post-contrast volumes. And finally, the provided ground truth has only the main lesion segmented. However, most cases were diagnosed as having multiple lesions, which made it complicated to evaluate our results. Here we show some example cases of this dataset, and as we can see, lesions had different sizes, shapes, locations, also intensity enhancements, which made it quite complicated. Moving to our proposed method. So regarding the inputs, we used the pre-contrast, the last post-contrast, and also the subtraction between these two. Regarding pre-processing, we first generated an ROI mask in order to exclude the confounding regions from the internal organs, since it's a source of false positives. So this way we could avoid having patches being extracted from this confounding region. Then all input volumes were intensity normalized. Then we extracted 3D patches in a balanced way to address the class imbalance issue, also with the restriction of the generated ROI. After that, the generated 3D patches were fed into a 3D unit architecture. Then the obtained binary segmentation was evaluated using the dissimilarity coefficient. Moreover, we investigated the use of different thresholds, optimizers, loss functions, patch sizes. We also compared the proposed architecture with another more complicated architecture used in one of the state-of-the-art studies. We performed 5-fold cross-validation, and for each fold there was 20 epochs, and the dataset was divided such that in each fold 9 to 10 cases were used as testing, and the remaining cases were divided into 80% for training and 20% for evaluation. Now, for evaluation, as I mentioned earlier, we use the dissimilarity coefficient denoted here by DICE1. However, having incomplete ground truth affected these DICE values and made them not completely indicative, since the secondary lesions will be considered as false positives even though they were correctly detected by our model. So this resulted in lower DICE values. That's why we calculated a second DICE denoted by DICE2, which is the DICE of only the primary lesion. And we did this just as a way to have a better indication of the performance. Now here we show some of our results, qualitative results. As we can see here, we're comparing using the basic unit architecture with 2 different patch sizes with another method from a recent study in which they used 2 hierarchical units. So as we can see, results show that using a basic unit provided better segmentation than when using the hierarchical units. Moreover, regarding the patch sizes, as we can see from the cases A and B, using smaller patch size provided better segmentation of most lesions and also better segmentation of the boundaries of the lesion. However, as we can see in case B, the smaller patch size resulted in more false positives. Now, the limitations of our study were that we used a small data set and all cases had lesions, so there was no healthy cases, and also they were all acquired with the same scanner. So in conclusion, we provided a fully automatic method which provided better results on the data set we used when compared with another more complicated method in a recent study. And also we provided 3D segmentation instead of a 2D, since in most existing works where they were performing only 2D segmentation. And finally, the results showed an improved segmentation of small and irregular, low enhanced lesions if to compare with the other method from the recent study. Finally, we believe that further improvements can be achieved using larger data set with complete annotation for those cases with multiple lesions, and also utilizing maybe information from more temporal scans, not just two. And finally, deploying other architectures, whether deeper architectures or modified architectures. Thank you, and hope to see you all in the workshop.